A storage pool is an elastic collection of physical drives belonging to a group of standard x86-64 servers running ScaleIO. Storage pools are software-defined and provide enormous operational and lifecycle advantages over traditional block storage. Operating systems and hypervisors need data storage. SANs abstract block storage using LUNs in a storage array. Arrays are nice because they provide reliability, performance, and capacity aggregation. LUNs are nice because they are OS agnostic and can support multiple operating systems and hypervisor clusters. ScaleIO provides a SAN alternative that abstracts data storage across a group of standard servers using what is called a storage pool. A storage pool is a set of hard disks or flash media distributed across a group of x86-64 servers connected over Ethernet. ScaleIO takes the local storage from the servers, abstracts it and pools it, and creates a redundant, high-performance, distributed, and shared storage system. This allows the applications on all the servers to utilize the storage on all the servers. Storage pool provisioning is managed through ScaleIO volumes. Volumes are analogous to LUNs. They are OS agnostic and support all the major operating systems and hypervisors. ScaleIO storage pools provide the benefits of a shared external storage array, but with simplified lifecycle operations, superior scalability and flexibility, and no expensive or proprietary hardware and networking. In this video, we will illustrate the advantages of storage pools and show a demo on a ScaleIO system involving the addition and removal of physical storage devices from a storage pool. Let's get started. Consider 6 typical servers in a data center, all running ScaleIO. These nodes may be from any server vendor, or they may be custom built. This visualization shows 2U Dell ScaleIO ready nodes with 10 gigabit Ethernet connections and direct attached storage. When the drives in these systems are added to a single storage pool, ScaleIO will abstract them and pool them. This creates a globally shareable pool with no silos of performance or capacity. This example shows a 3-node ScaleIO cluster where each node contains 8 SSDs and 16 spinning drives. Since ScaleIO aggregates performance and capacity, this system would likely have 2 storage pools, one consisting of flash media and the other consisting of spinning media. As this example shows, ScaleIO nodes may contribute storage to multiple storage pools at one time. This example also illustrates how storage pools can support any media type, including hard disks, SSDs, and PCIe flash. Each pool maintains its own even data distribution, client I/O distribution, and available free space. Hardware-based read and write caches, as well as RAM read caches, are shared and aggregated along with the underlying media. This results in a very high-performance distributed storage system. Storage pools do not need to be homogeneous across servers. For example, the 3rd node in this illustration might contribute 5 SSDs to the all-flash storage pool instead of 8. Storage pools allow complete flexibility over deployment of your hardware resources. This video, however, illustrates homogeneous storage pools for visual simplicity. Storage pools allow an administrator to dynamically move physical drives as business requirements change or when bursting capability is needed. This 6-node cluster has 2 storage pools made up of spinning media, one dedicated to a finance group and another dedicated to a marketing group. Finance and marketing both use the storage continuously for their applications. Finance, however, needs to burst storage performance for end-of-quarter processing. Some of the physical media that makes up the marketing storage pool can be moved to the finance storage pool. This will increase the performance of the finance storage pool. These servers contain SSDs as well as spinning media. These SSDs are available, so they can also serve as a read cache. Addition of the read cache will further accelerate the finance storage pool. Once the end-of-quarter processing is complete, the administrator can return the stored resources back to their original configuration. ScaleIO balances user data evenly across all the drives that make up a storage pool. In this 3-node example, all the drives are part of a single storage pool, and they're about 70% full. A new node is added. When the drives are added to the storage pool, all the nodes and devices taking part in the storage pool work in parallel to balance the user data across the drives. The majority of the data remains in place on the old drives. A minimal amount of data is moved to populate the new devices added to the storage pool. This even data distribution, coupled with the ScaleIO client's built-in multipathing, eliminates bottlenecks, hotspots, and silos. This balanced and meshed design results in very high throughput and very low latency. As additional nodes are added and their drives are added to the storage pool, the system can recover from failures more rapidly, as there is proportionally less data to reconstruct if a node or drive is lost, and there will be more nodes working in parallel to reestablish data protection. When drives are manually removed from the storage pool, a similar operation migrates user data to the drives that will remain in the pool. Once the data has been migrated off the drives, empty nodes can be removed. Unplanned node or drive failure results in a similar self-healing operation. This self-healing operation reestablishes data protection in the same distributed, balanced, and minimal way. Because storage pools maintain the structure and protection of user data as physical drives are added or removed, a ScaleIO system can expand or contract at any time. Storage or storage and compute can be added to the system quickly as demands increase. Similarly, as hardware is decommissioned or if requirements decrease, nodes can be removed. These streamlined lifecycle operations allow enterprises to achieve the same operational efficiencies that hyperscale cloud providers enjoy. Storage pools reduce installation and deployment timelines, eliminate large upfront investments for future usage, provide predictable performance and resiliency at scale, and reduce operational cost and risk. Storage pools can span multiple racks, and they reside inside protection domains. Protection domains are groups of servers that provide fault isolation in a ScaleIO cluster, which may consist of thousands of nodes. If you're interested in learning about protection domains, consider watching our video on them after you finish this video. This video features an 8-node ScaleIO cluster running on ESX. It has 3 storage pools, A, B, and C. In this demo, we will assume that each storage pool houses data for a separate tenant, with marketing using storage pool A and finance using storage pool B. Storage pools A and B reside in protection domain 1. This protection domain is made up of all flash nodes. Storage pool C, which we will not modify in this video, resides in protection domain 2. Protection domain 2 is made up of nodes that house spinning media. At the start of this demo, storage pool A will be 22% full, and storage pool B will be 76% full. With the system under load, we will move flash capacity from the marketing storage pool, A, to the finance storage pool, B. First, we will remove 5 SSDs from storage pool A. The storage pool will then rebalance, migrating user data and data protection off the drives to be removed. The capacity of storage pool A will decrease. It will go from 22% full to 27% full. Once the SSDs have been evacuated, we will add them to storage pool B. Storage pool B will then rebalance, distributing user data and data protection evenly across the drives. The capacity of storage pool B will increase. It will go from 76% full to 38% full. Note that on a production system of this size, all the SSDs in the first 5 nodes of the cluster would likely be in the same storage pool, as ScaleIO supports QoS, and a volume can be used by any hypervisor, operating system, or tenant regardless of which storage pool it resides in. We'll begin the demo on the ScaleIO dashboard. Here we see the total capacity available to the cluster, the number of protection domains, and the number of storage pools. This system is actively servicing a workload consisting of both reads and writes. Let's take a more detailed look at the storage pools. Storage pool A is about 22% full. Storage pool B is about 76% full. Storage pool C resides in protection domain 2 and it's about 20% full. Storage pool A is using 5 SSDs from each of the 5 nodes that make up the protection domain for a total of 25 SSDs. Capacity, IOPS, and redundancy are evenly distributed across flash drives in this storage pool. Every physical drive is evenly utilized as the capacity icons illustrate. Storage pool B consists of 5 SSDs, one on each of the 5 nodes that make up the protection domain. As with storage pool A, capacity, IOPS, and redundancy are evenly distributed across every flash drive in this storage pool. But unlike storage pool A, these devices are nearing their capacity limits. With ScaleIO, the physical storage devices are all under software control. We can easily move devices from the underutilized pool to the overutilized pool where that capacity will be needed. To do this, we're going to remove some SSDs from storage pool A. This will free up the SSDs for addition to storage pool B. As we remove the devices, the data will be rebalanced across those devices that remain in the pool. Let's remove 5 SSDs from the first storage pool. This warning message tells us that the physical device will still be mapped to the ScaleIO virtual machine, even though we are removing it from the storage pool. That's what we want, so we click OK and continue with the remaining devices. During the rebalance operation, all the nodes contributing storage are rebalancing to all the other nodes contributing storage. The individual disks in each of these nodes are also working in parallel to speed up the operation. The rebalance operation is complete. Storage pool A, the marketing storage pool, now consists of 4 drives from each of the 5 servers for a total of 20 SSDs. The system is continuing to serve I/O, and as before, load, capacity, and redundancy are distributed across all the drives in the storage pool. Storage pool A is now about 27% full, and we have 5 available SSDs to assign to the finance storage pool B. We'll enter the name of the device in the destination storage pool for each of the SSDs. ScaleIO will now add these new SSDs to storage pool B and begin a rebalance operation to level out the utilization of the storage pool using both the old and new SSDs. The new SSDs have been added to storage pool B, and a rebalance operation has evenly distributed the data across the SSDs. Storage pool A is now about 27% full, and storage pool B is about 38% full. The marketing department's underutilized capacity was moved to the finance department without manual rebalancing. The user data and data protection relationships remained intact while the SSDs were moved from one storage pool to another with the system under load. Similar procedures are used when adding new nodes to a ScaleIO cluster, removing nodes from a ScaleIO cluster, repurposing nodes or storage devices, or bursting a workload. Storage pools contain client volumes that are analogous to LUNs. These volumes can be accessed by the operating systems or hypervisors contributing raw storage, or the volumes can be accessed by other servers. As with LUNs, these volumes can be used by any group of hypervisors or bare metal machines. Storage pools are elastic allocations of physical drives. They can grow or shrink as demands change, as hardware is acquired, or as hardware is decommissioned. Storage pools aggregate flash media or spinning media, providing enormous capacity and performance. They are media agnostic and therefore future-proof. They support spinning media, SSDs, and PCIe flash, and are designed to take advantage of emerging forms of persistent storage. Storage pools can provide shared, distributed read and write caches, fully and evenly utilizing the hardware available to the system. Storage pools evenly distribute client I/O and capacity. This provides consistent performance for the applications that use the storage, and it eliminates hotspots. Storage pools are self-balancing. This reduces operational burdens associated with data growth and new system procurement, and provides a rapid return on new hardware investment. Finally, storage pools are software-defined and can be modified on the fly. They are not subject to the constraints inherent to hardware-based approaches. Storage pools are a scalable and flexible alternative to traditional storage architectures and bring the efficiency of hyperscalers to the enterprise.